All right, so we've already learned that there's an electromagnetic spectrum and that it ranges from lowest frequency of radio waves to microwaves to infrared to visible light to ultraviolet to X-rays to gammas, which are the highest frequency, and that visible light can be separated out into its spectrum, where the lowest frequency is red, and then orange, yellow, green, blue, indigo, with violet as the highest frequency. And that the frequency of these lights, of these types of light or electromagnetic waves, is constant. And the way that we find them is we take the speed of light in air and we divide it by the wavelength of the light in air. And this is a constant value no matter what substance we go into. So for example, if we had a 700 nanometer wave, its frequency, and that would be red light, that would be 3e to the 8th meters per second divided by 700 e to the negative 9 meters. 3e to the 8th divided by 700 e to the negative 9 is going to be 4.29 e to the 14th hertz. 4.29 e to the 14 hertz. And so that frequency, whether it goes into water or diamond, will be the same. But what does change is the speed. And so when this red light hits this interface from space into some medium, it is going to slow down. And if you think about the wavelengths in air, they might look like this. Now they're going to go into an electromagnetic field that is denser, and they are going to shorten, because it's going to basically cause them to bunch up. And the result is that they bend, and that this angle that we call the angle of incidence, whatever angle it hits that interface with, it's going to bend so that the angle of refraction, which is the bending of light as it goes into a new substance because it slows down, the angle of refraction is going to be smaller than the angle of incidence. Now, the amount that it slows down is given by something called the index of refraction, which has a symbol of N. And it is equal to the speed of light divided by whatever the speed in that substance is. So let's say that this substance is a diamond. And I want to know how fast light is traveling in that substance. Well, it turns out that you can look up the index of refraction for a diamond in a chart, and it's in your readings in the chapter on this. There's a table of them, and there's one on the next slide. It turns out that the index of refraction for a diamond is 2.417. So if I want to know the speed of it inside of a diamond, I'm going to take 2.417 and set it equal to 3e to the 8th meters per second, and then I'm going to solve for v. So v is going to be equal to whatever c is divided by n, or 3e to the 8th meters per second divided by 2.417. If I put that into my calculator, I'm going to get 3e to the 8th divided by 2.417. And that's going to give me 1.24 e to the 8th meters per second. So that's the speed of light. So remember, we had found earlier that the frequency of a 700 nanometer ray of light in air was 4.29. So frequency in air of a 700 nanometer was 4.29 e to the 14 hertz. So what that means is that, remember that in our diagram here, the wavelength, which is 700 nanometers, is the wavelength in air. okay? And when it goes into, or vacuum, when it goes into that diamond, the diamond is more dense electromagnetically. And that wavelength is going to decrease as it goes in, and that's going to cause it to bend. So let's find the new wavelength inside of the diamond. So to do that, we're going to take the speed of light in a diamond and the frequency of that wave there, and we're going to multiply it by the wavelength in a diamond. So the wavelength in the diamond is going to be equal to the velocity of it in the diamond divided by the frequency. Well, the velocity of it is 1.24 e to the 14 hertz. And the frequency of it, if I remember correctly, is 4.29 e to the 14 hertz. And the velocity of it, I screwed that up, sorry, is e to the 8th meters per second. So we're going to put these in our calculator. 1.24 exponent 8 divided by 4.29 exponent 14. And we're going to get a wavelength in diamond of 2.89 e to the negative 7. 2.89 e to the negative 7, or 289 nanometers. So remember that I said when it goes into a more optically dense, which is something that has a high N, that the wavelength is going to decrease, but the frequency stays the same. So it's still red light. All right. So let's talk a little bit about how light bends as it goes into smaller and smaller indexes. So first of all, let's go from air. This is air, which has an N of 1. So that means it's traveling at the speed of light. And this is, say, something that has an N that's bigger, 1.33. A bigger N means a slower medium. And then it's going to go back into air. So what's going to happen is we're going to consider where it's hitting, and we're going to draw a line perpendicular to the surface. And we're going to measure this angle here. This is the angle of incidence. And that ray is going to slow down, and that is going to cause the ray to bend towards the normal. That's what this line is. It's called the normal. It's an imaginary reference line. And notice that this is our angle of refraction. Refraction just means bending of light. And as we go from a low N to a high N, the velocity is going to decrease, and I will be greater than R. It's going to bend towards the normal. Then when we go back out into the air, which has the same index as before, 1.00, it will speed up by the same amount that it slowed down by. So this will be the same. So this will be our new angle of incidence, will be whatever it refracted at inside, because they're parallel, opposite interior angles are equal. And it's going to be equal to that original angle that it went in at. So when you go from a low N to a high N, velocity slows down. When you go from a high N to a low N, the velocity speeds up, and the angle of incidence is going to be less than the angle of refraction.